Continuing on in section 9.1 here, we're going to graph y equals ax squared plus c. We want to know how is the graph of y equals ax squared plus c different from the graph of y equals 2x squared. So we're going to start at y equals 2x squared. And in order to graph this, we're going to use our table of values. And I'm going to pick points like -2, -1, 0, 1, and 2. And I'm going to plug those in. So I'm going to take 2 times -2 squared. Again, these are my x values. I plug them in for x. Again, I'm just plugging them in for my x value, or x in my function. And again, when we have negative numbers, we want to make sure we put those in parentheses. So it's a good habit to always put them in parentheses if you want when you type them in your calculator, just to make sure that we are getting where we need to go. So here, I'm going to be at -2, 8, -1, 2, 0, 0, 1, 2, and 2, 8. And we connect our dots. Again, remember we're going to want these to be curved. The dots are the important part because those are going to show us where we're at. And then we're going to do our best to connect them with a curve. And then we want our arrows to go out. Okay, we don't want them to come back in. Now, our second equation here is the same as our first one, but we have a +3 at the end. That's the only difference. So since we already did the first part, I'm just going to add 3 to all these. So 8 plus 3 gives me 11. 2 plus 3, 5. 0 plus 3 is 3. 2 plus 3, 5. 8 plus 3, 11. And now my new ordered pairs are there. So at -2, I go up to 11. At -1, I go up to 5. 0, up 3. 1, up 3. And 5. Or sorry, 2, up 3 more. And we can connect our dots. And again, we want that to go out. So if we compare our graphs, the graph of y equals 2x squared plus 3, it's like we have the exact same graph here. It's like I just picked up my graph and moved it. So instead of being here, it's like I just picked it up and moved it. Okay? Now it's like the same graph. It's like I just picked it up and moved it. Okay? So we call that a translation. So the graph of y equals 2x squared plus 3 is a translation of y equals 2x squared translation up 3 units, of y equals 2x squared. Or you could say the graph of y equals 2x squared plus 3 is the graph of y equals 2x squared translated up 3 units. However you want there, just make sure that we're using both equations so we know how they're compared. We start here and then move to there. So this graph is a translation of this graph. We say translation, that's how it was changed. It was just moved, and which direction and how many units. So they're like the same thing here, guys, just moved up. And that's because that +3 only changed our y value there. Now, feel free to pause here and give this a try if you'd like. We want to know how are these graphs related. We're going to graph both of them first. but we wouldn't need to. Just looking at our equations, we see that the only difference here is a -3. And since that's at the end, we know that it's going to go and just change our y to be 3 less. But we'll go ahead and graph these here. First, this is our parent function. So these values you should get comfortable with because these are going to be our baseline values. And any quadratic can be graphed using the parent function, this one that I have right here, using transformations. So either translations or reflections, which is when it goes from positive to negative, stretches, which we talked a little bit about in the first part of this section, and compressions. So here is my parent function. Now, we have this -3 at the end. So I'm going to take and I'm going to subtract 3 from each of these. So 4 minus 3, 1. 1 minus 3, -2. 0 minus 3, 1 minus 3, 4 minus 3. And now I have new ordered pairs. -2, 1. -1, -2. The other thing we could do, guys, is once we have our graph and we know what our transformation is going to be, we can move all of those down 3. Our y's are going to be 3 less. We go down 3. And those values match the same ones I got for my ordered pairs over here. Connect our dots. And there we go. How are the graphs related? Well, the graph of y equals x squared minus 3, it's the same, so it is the graph of y equals x squared, but it's been translated down 3 units. And that's because it's negative. So because it's negative, guys, we went down. We said like subtract it, or y got lower. Okay? We can use the function h equals -16 t squared plus c to model an object's height h after falling t seconds from an initial height of c. In example 5 here, we're going to use the following object model. An acorn drops from a tree branch 20 feet above the ground. The function h equals -16 t squared plus 20, here that 20 is because that's my initial height, gives the height of the acorn in feet after t seconds. What is the graph of this quadratic function? And at about what time does the acorn hit the ground? So here, my function, h equals -16 t squared plus 20. I'm still going to make my input-output table here, guys. So instead of x and y, though, my x is a t, and my y is an h. When we go to plug in our values here, guys, we have to consider what our variables mean. Here, t, or our inputs, our x value, is time. We can't have negative time. So we're going to start at 0, 1, 2, 3, 4, 5, and go on until we find the values we're looking for. And our h value is a height. So our height also can't be negative. An acorn can't drop to a height of -10 feet, right? It can drop to the ground, which is 0 feet, but it cannot drop any lower than that. So we need to be on the lookout for that as well. Keeping that in mind, we really just need the first quadrant of our graph now. Okay, we can only have answers in the first quadrant. We have time on our independent and height on our dependent. So when I substitute in here, I'm still going to plug in for my independent variable here, and I get 20. So at 0, I'm at 20. Change colors here so you can see it. At -16 times 1 squared plus 20, I'm at 4. So at 1, I'm at 4. -16 times 2 squared plus 20 gives me -44. I can't have a height of -44, but it does tell me that my graph's going to be way down. So it helps me shape my graph. But again, we're still only going to draw it in this first quadrant. Something kind of like that. Again, keep in mind that this is curved the best we can there. Now, we need to know at about what time, sorry guys, at about what time, so it's a curve, and it's going to drop down and go through for, this is my last one. We're just going to go with what I got here. Kind of. Okay, I'm not any better on here than I am on the board. At about what time does the acorn hit the ground? Well, if we look here, we know it's a little bit after 1 second, not to 2, and we know it's not going to be to 2 until way down below. So here, a little after, or slightly after, or just after, something like that, 1 second. But we want to be a little bit more specific than saying after 1 second. We want to know like how close to 1. Here it's just after, or a little bit after. Now, suppose the acorn drops from a tree branch 70 feet above the ground. The function h equals negative 16 t squared plus 70 gives the height of the acorn in feet after t seconds. What is the graph of this function? And then, at about what time does the acorn hit the ground? So again, we're talking time and height. So when you draw your axis in, you can draw it just on for the first quadrant. My input is t, my output is h. So instead of x and y, those are the variables I'm going to use. Again, because we're talking time, we can't have negative values. And I would suggest that we graph as we go, because like in the last example, there were only 2 points we could graph. So we didn't need to calculate all of our values. So if we go as, this is a 0. As we go, if we graph those points, it'll save us some time by getting values that we can't actually have. Negative 16 times 1 squared plus 70. It's going to give me 54. Negative 16 times 2 squared plus 70. It's going to give me 6. So at 2 seconds, I'm at 6. This is going to give me negative 74, I think. Which is going to be something we can't have anyway. So we can't have any time, at least 3 is too long. So here, we're going to draw in our line, and that is our graph. And again, the function that we have here, if it wasn't being applied, if we didn't know what t and h stood for, we could put arrows here, we could draw the other side, but because we know this, we can't put any arrows, and we're just drawing in the first quadrant, because we can't have negative time, can't have negative height. Now, we want to know at about what time does the acorn hit the ground? And it's right here, which is just after 2 seconds. So slightly after 2 seconds. Real quick recap here. The family of quadratic functions model certain situations where the rate of change is not constant. Quadratic functions are graphed by a symmetric curve with the highest or lowest point corresponding to a maximum or minimum value. And that's all I have here for section 9.1.